Let's go to this title, stability and determinacy. What do you mean by stability and what do you mean by determinacy? These are the questions we are going to try to get the answer. Okay. Consider these equations of equilibrium for a coplanar force system. Coplanar means what? It's a same plane. Some force is acting. The force system is lying in this plane. That's why it's called coplanar system. Coplanar system, F-x horizontal direction, Fy vertical direction, and moment about any point, that should be, all these things should be zero. That means no unbalanced force is there. If any unbalanced force is there, that would act just like to make this body to move in that unbalanced direction of force. That's our Newton's second law. Okay, here let us see the summation of Fx is nothing but summation of the x components of each force in the system. For example, this one. If it is in this direction, if it is in this direction, it cannot be in equilibrium because it will try to pull here, it will try to pull here somewhere, resultant it will be there. But if you see this one, these two are in the opposite and same collinear line, so it will be in equilibrium. Here also, if you see multiple forces are acting on, it cannot act like that. It will try to, the unbalanced force, it will try to rotate it. If it needs to be in equilibrium, all these forces should pass through common concurrent point. Then only it will be in equilibrium. Here we can see these support structures. Sometimes structures are either partially or completely restrained so that they cannot move freely in space. That means what? Like we can completely restrain means it's like arresting its movement, rotation, and translations. That's called restraining. Such restraints are provided by supports that connect the structure to some stationary body, such as ground or another structure. What does it means that, like, if we have one rectangular bar, something like that, if we have some arrangement that restrains its movement to lateral or vertical, that kind of restraining or limiting its movement is called some support conditions. Okay, so once you restrain something, there will be some reactions. So that's how it's developing it. We will see what are the hinge support and what are the reactions it would develop. All these things we can see it here. It can be considered like a ground or another structure where it is giving some restraints. The first step in structural analysis is to take the structure without supports and calculate the forces known as reactions exerted on the structure by the supports. That means what? For example, a hinge support is represented by a symbol like this hinge support, or like this also we can represent. It can resist the general force P in any direction, but it cannot resist the moment of the force about that connecting point. For example, this point, if you see it, if we apply some load, it will try to rotate it. That means what? It is not restraining the rotation, only it is arresting the lateral and vertical movement. This kind of support is called hinge support. The reaction of the hinge support is assumed through the center of the connecting pin. You can see this is the pin point. So at that center, it is all these reactions are passing through. That's how we are assumed it, and it actually participates like that only. Its magnitude and slope of the action of lines are to be determined. See, for example, Rx and Ry, we can see it like this: Rx lateral, Ry is vertical. Resultant is it will come like this. Based on if Ry is more, this angle will be towards vertical. If Rx is more, that angle will be almost towards the resultant that will try to go horizontal. It will be like a flat. That's how we can see this Rx and Ry. This is theta is right, opposite by adjacent. Tan theta we can take. That's how it is taken, like tan theta equal to Ry by Rx. So theta is nothing but tan inverse of Ry by Rx. X component of R and Ry is Y component of R. Theta is the angle between the R that makes with X direction. Theta X. Okay. We will see how the reaction develops, how we can calculate the components of reactions, the direction of the reaction, all these things we can see it. There's a hinge support. You can see hinge support can also be replaced by two links along the horizontal and vertical directions. This is the horizontal direction. This is the vertical direction. It can be replaced by two links through the center of connecting pin. This is the connecting pin center. Through this point, it can be replaced. That hinge can be replaced into two different links, as shown in this figure 2.4a. Each link is a two-force member, the axial force of which represents the element reaction Rx or Ry. This is the axial force of this link. This is also axial force of this link in x direction. For this link, this y direction, axial force is the. And in general, the hinge support is equivalent to two supporting links provided in any two different directions, which are not necessarily an orthogonal set. It means that it's always not necessarily to be an orthogonal direction. It can be at any direction in this link and this link. Okay, through the connecting joint, as one where R1 R2 indicate the axial forces in the two links. The reaction R at the pin can always be determined if the magnitudes of R1 and R2 are obtained. We can find out the reaction once we know this R1 and R2. In this one, we will see roller support. What is roller support? Roller support is represented by either a symbol like this with one dot here and two like a roller kind of things, or one horizontal line with this kind of symbol. Either of these two symbols, roller support is represented by either the symbol like this or like this. The support mechanism used is such that the reaction acts normal to the supporting surface through the center of the connecting pin as shown in figure. What does it mean? This means that this is the surface where it is getting supported. So always this will produce the reaction like this. And if it is supported like this, roller is like this, it will restrain, it will only in this direction. It cannot restrain in this direction, it will start moving it. Here also it will start moving like this, but it will restrain this one. And this can be a link support shown in figure 2.5d is also of this type, since the link is a two-force member and the reaction must be along the link. Link is a two-force member and the reaction must be along this link. Fixed support. A fixed support is designated by the symbol like this. A fixed support is designated by a symbol like this. It is capable of resisting force in any direction and moment of a force about the connecting end. It is capable of resisting force in any direction. Force in any direction means Rx or Y or any inclination. That is the force in any direction. It is capable of resisting force in any direction and moment of force about the connecting end. Because of this force, it will produce a moment, turning effect. So it is resisted by this fixed support. So moment of force about the connecting end is capable of resisting, thus preventing the end of the member from both rotation, translation and rotation. Thus this end, the end of the member is prevented from both translation and rotation. Like this, it cannot rotate like this. Okay. So here you can see resultant is nothing but square root of rx squared and ry squared and theta x tan inverse theta x equal tan inverse of ry by rx. The two devices equivalent to the fixed support are shown in the figure. Each is composed of a hinge and the roller and represents three elements of reaction capable of resisting both force and moment. Here if you could see here, this support can resist one vertical force and one horizontal force. This also one vertical force can restrain. If I apply something like this, what will happen? It will try to produce the moment here, but it will be resisted by this force and this force. That means this distance, it would act like a force and distance lever arm. That would be the resisting moment for this external force. Whatever the moment caused by this external moment is resisted by these two reactions, these two support reactions, because they are separated by a small distance lever arm. That would create the resisting moment. So this structure is capable of resisting vertical and lateral as well as moment. So this can be considered as equivalent to this fixed support. At the same time, if you see it here, if I apply load here, what would happen? It will try to come down, but at the same time, these two elements, this one will take tension, one will take compression. That way it is capable of resisting the moment. At the same time, it will resist this along this direction forces. This link will resist the forces along this direction, because all these links are axial resisting members. These two are equivalent to the system of this bending moment free cantilever system for fixed support system. In this section 2.3, we will study about internal forces at a cut section of a structure. Here we will see this one. A truss structure is composed of a pin connected members. That means what? This, for example, one member, if you take it, this member at both ends, the pins are used to connect the one member to another member. That's what is explained here. The truss is composed of pin connected members and is assumed to be pin loaded, and loading also happens at the pin locations. That's how it is designed. It is assumed to be a pin loaded as shown in figure 28a. Now if any one of the members is taken from its connecting pin as a free body, we will take one member from this one, taking as a free body. The forces exerted on the member must be concentrated at the two ends of the member through the center of pins. That's what these forces should be concentrated like this. At this location, we'll be having one member like this, one member like this, one force is like this, another force is like this. And at this location, if you see it, these two are the external forces, this force and this force, and this member internal force is represented by like this, and this member force is represented like this. That is this way. Okay. The forces exerted on the member must be concentrated at the two ends of the member through the centers of pins. Through the centers of the pins at the two ends, it's getting concentrated. Furthermore, these two systems of concurrent forces can be combined into a resultant force that must be equal and opposite and collinear. And this can be represented by a resultant force. This also could be represented by a resultant force. These two should be, in other words, these two must be equal, opposite, and collinear. It's equal and opposite and collinear. Equal means the magnitudes are equal. Opposite means this goes downward direction, this goes upward direction, inclined about upward. And in the same line, it's acting. That's called its collinear, as indicated in figure 28b. In other words, each member of a truss is two force member. Each member of the truss is a two force member, means one force at this end, another force at that end. It's a two force member. Hence, the internal forces existing in any cut section of the truss member, assumed straight and uniform, must be a pair of equal and opposite axial forces to balance the axial forces exerted on ends as one. What does it mean? If you take a cut section here, at the cut section, internal forces existing in any cut section of the truss member must be a pair of equal and opposite axial forces. 1 and 2. This is the pair, and equal and opposite axial forces to balance these axial forces exerted at the ends. That's clear. Okay, as shown in figure 28c. The fact that each member of a truss represents an unknown element of the internal force enables us to obtain the total number of unknown elements of the internal force by counting the total number of members of which truss is composed. What does it mean? Fact that each member of a truss represents an unknown element in internal force. So in each member it has one unknown internal force. So by counting the total number of members of which the truss is composed, total number of members, this truss is composed of 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 numbers. So 8 internal member forces are unknown, and of course reactions also unknown. That's how we can, that will enable us to obtain the total number of unknown elements of each internal member force by counting the total number of members in which the truss is composed. Let us read this. Member of structures such as beams and rigid frames. This is beams and this is rigid frames are acted on by more than two forces. These are acted upon by more than two forces. Let us investigate the elements of internal force in any cut section AA of the beam in figure 2.9a, or if the rigid frame in figure 2.9b. What does it mean? That means this is the beam, this is the frame. At this cut section, we are going to investigate the elements of internal forces. Here, if I take a cut at section A, let us see it like this. We begin by taking the free bodies of the portions to the left and right section of the A. If I take a cut here, we will take the free body of this left side portion and this right side portion. So in this free body diagram, this fixed support, it will have two reactions. This is the vertical force, this vertical force. At this cross section, what are the four internal forces and moments are developed? You can see one axial force and one vertical force and one moment. These are the internal forces, and the same thing should be on the right side to this section A, cut section A, so that it would be in equilibrium. So here it is obvious that forces of internal constraint must exist between these two portions in order to hold them together. These two are held together. Okay, so if we cut this one, forces should be equal in order to hold them together. Such internal forces, of course, always occur in pairs of equal and opposite forces. That means if I have a shear in downward direction, here's here upward direction, equal moments in opposite direction. Axial force is from left to right, and here for this one from right to left, and equal magnitude and opposite to the direction, right? Equal and opposite forces. The moment also same way, this is in this anti-clockwise rotation and this clockwise rotation. These two will be the, if I sum of these two, it will be 0, so that it will be equilibrium. So that's what it means. Always occur in pairs of equal and opposite forces. The actual distribution of the internal forces cannot be easily discovered. Yeah, actually these forces cannot be very easily discovered. To maintain the equilibrium of the free body, however, the internal forces must be statically equal and opposite to the system of forces acting externally on the portion considered. If I consider this portion, it should be in equilibrium. So whatever these reactions coming, because of these forces and inner forces, it should be in equilibrium. So if we take a force about this point, moment about this point, this vertical load will produce some clockwise moment, and this force V will produce anti-clockwise moment, and this moment also anti-clockwise moment, and N is not producing anything because it's passing through that, so it will become 0. Okay, to maintain the equilibrium of the free body, however, the internal force must be statically equal and opposite to the system of forces acting externally on the portion considered. And the internal forces can always be represented by a force applied at the centroid of the cross section together with a couple of moments. Yeah. Furthermore, a force can in turn be resolved into normal component and tangential component. Thus, in figure 2c and D, we represent the stress resultant on section AA by three unknown magnitudes: axial, shear, and moment, called respectively the normal force, shearing force, and resisting moment at the section. Equations of condition or construction. What do you mean by this one? Let us explain in detail. The structures such as trusses, beams, and rigid frames may sometimes be considered to be one rigid body sustained in space by a number of supports. Out of several such rigid bodies, a compound form of structure may be built by means of connecting devices such as hinges, links, and rollers, and mounted on a number of supports. In either the simple or compound type of the structure, the external force system of the entire structure, consisting of the loads on the structure and the support reactions, must satisfy the equations of equilibrium if the structure is to remain at rest. However, in the compound type of structure, the connecting devices impose further restrictions on the force system acting on the structure, thus providing additional equations of statics to supplement the equations of the equilibrium. Equations supplied by the method of special construction or other than external supports are called equations of conditional construction. We discuss these further in section 2.6. This entire thing is nothing but if you have any internal hinges, because of the construction, we will get additional equations of equilibrium. For example, if you have one simply supported beam or a fixed beam with support at the end, proper cantilever, if you put one internal hinge at the middle, that would give us one more additional support equations of equilibrium. That is called equations of condition or construction. Here, stability and determinacy of a structure with respect to supports. Two elements of reactions supplied by supports, such as two forces, each with a definite point of application and direction. This is important, point of application direction, are not sufficient to ensure the stability of a rigid body because they are either collinear, parallel, or concurrent. So, because of the two are either collinear, parallel, or concurrent, that will become stability problem. In each of these cases, the condition of equilibrium is violated, not because of the lack of strength of supports, but because of insufficient number of support elements. It's not because the lack of strength of supports, it's because of insufficient number of support elements. This situation is referred to as statical instability. Statical instability. If you see this location, this figure, force is acting like this. This would produce the reaction only in the vertical direction. So because of this horizontal force, it will start move in this from left to right direction. This is called statically unstable structure because these two reactions are collinear, parallel, right? So it cannot restrain any horizontal movement of structure because of this force. In this figure, you can see these two supports are providing vertical parallel reactions, but the force is horizontal directions. So this cannot also resist the move lateral direction of translation of the structure due to this force. This is also an example for statical instability of the structure. Here you could see these support reactions are concurrent to this point O. So any force acting like this, it would produce a moment of this force times the perpendicular distance between O and this line of action of this force. That moment is not restrained by any of these two supports. That means it would cause the structure to rotate like this. This is also an example for statical instability because the forces are concurrent at point O. Reactions are concurrent at point O. Force is not passing through the line of reactions. Okay. So there is some unbalanced moment would be caused that would make the structure as a statical instability structure. This example, you can see that this hinge it would act on vertical force and horizontal force, but this is acting in this direction. This line of action of this force and its perpendicular distance, it would cause moment about this force. This pin support cannot restrain the moment, so it would make the structure to tilt or rotate in this direction, anti-clockwise direction. This is also an example for statical instability. In this slide, we could see structures stable under special conditions of loading but unstable under general conditions of loading are said to be in a state of unstable equilibrium and are classified as unstable structures. In figure this 211a, the applied loads acting on the body are themselves in equilibrium. Therefore, no reaction is required. In figure 211b, in this figure, the applied load is in the same direction as the reaction, so equilibrium can be maintained for the parallel force system. In figure C or D, the applied load is through the concurrent point O. Therefore, equilibrium can also be established. This applied load is through the concurrent point. Applied load is through the concurrent point. Therefore, equilibrium can also be established. Structures stable under this kind of special conditions of loading, but unstable under the general conditions of loading are said to be in a state of inequilibrium, unstable equilibrium, and also they are classified as unstable structures. Here you could see at least three elements of reaction are necessary to restrain a body in stable equilibrium. Consider each of the cases shown in this figure. The rigid body is subjected to restraints by three elements of reactions, and the restraints can be solved by three available equations of equilibrium equations. The satisfaction of all the three equilibrium equations, summation f x equals 0, f y equals 0, moment equals 0 for loads and reactions acting on the body guarantees respectively that the body will neither move horizontally or vertically nor rotate. The system is said to be statically stable and determinate. Only here, for example, 2 plus 1, 3 reactions are there, 3 equilibrium equations. So we could easily calculate these unknowns by applying purely equations of equilibrium, 3 equilibrium equations. So this is called statically stable and determinate structures. The system is said to be statically stable and determinate. If there are more than 3 elements of reaction, as in each of the cases shown in figure 3, the body is necessarily more stable because of the additional restraints. We have 3 reactions plus additional 2. So because of these additional restraints, the body is necessarily more stable. That's what explained in these first two sentences. Okay. Since the number of unknown elements of reaction is greater than the number of equations of static equilibrium. So here, number of unknown elements of reaction. This one element of unknown reaction, another element of reaction. These two are additional. Okay, this unknown number of reactions, elements of reaction here 2, 3, 4, 5 are greater than the number of equations of static equilibrium. Number of equations for static equilibrium is 3. So this system here also 3 reactions, 4, 5 reactions. Here also 3 and 4, 5 reactions. So the unknown elements of reaction is greater than that of the number of equations of static equilibrium. So the system is said to be statically indeterminate with regard to reactions of support. These are the support and these are the reactions of the support. With regard to the reactions of the support, the system is said to be statically indeterminate. One thing we should note is that number of elements reaction should be at least 3 is a necessary but not a sufficient condition for externally stable structure. For example, in this one we have 4 reactions. All these 4, more than 3 numbers of reactions are there, but it does not mean that it is sufficient condition to make the structure externally stable. See, there are many cases that are obviously not stable with respect to the support system. You have to understand that with respect to the support system, we are evaluating the stability of this structure, externally stable or not, even though 3 or more than 3 elements of reactions are supplied. 3 or more than 3. For example, here this reaction is parallel, this reaction is this, all these 4 reactions are parallel. So this, when the, for example, the lines of reactions are all are parallel, as in this figure, the body is unstable because it is vulnerable to the lateral sliding. Another case is that in this, here you can see it, where the lines of 3 reaction elements are originally concurrent at point O. The system is unstable because even though the complete collapse probably will not result, a small initial rotation about O because of the moment caused by any force not acting through the O will certainly occur until the three reaction lines form a triangle indicated by a crossed hatch lines. So these two, at this point, these two reactions are concurrent, but this is not concurrent. This is passing through. This is not at the same point it is passing. It is passing in different point. So this will start resisting the unbalanced moment. So once that point of time, the structure will be stable. If all these 3 reactions are once again passing through this O because of any unbalanced force, once again it will start rotating it. So once if it start initial rotation, then the reaction direction will change. So at this point, O, these two forces only concurrent, but that force is not concurrent. So that will make the structure to be stable. So the above mentioned instability, which results from the inadequacy of arrangement of supports, is referred to as external geometric stability. Here we could see general stability and determinacy of beams. This structure is stable and this structure is also stable. Alright. If a beam is built without any internal connections, that is internal hinge or roller, the entire beam may be considered as a single monolithic rigid body placed on a number of supports. And then the question of the stability and the determinacy of the beam is settled solely by the number of arrangement of supports. Now let us investigate what will happen if certain connecting device is inserted in the beam. Let us suppose that the hinge is introduced into a determinate beam, statically stable and determinate beam. The beam in each case will obviously become unstable under general loading as a result of relative rotation between the left and right portions of the beam at the internal hinge, as indicated here, that the hinge has no capacity to resist moment. The hinge has no capacity to resist any moment. That the hinge has no capacity to resist moment constitutes a restriction on the external forces acting on the structure, that is M equals 0 about the hinge. In other words, the moment about hinge calculated from the external forces on either side must be 0 in order to guarantee that these portions will not rotate about the hinges. Referring to this figure 2.5 C and D, we see that in each case there are three elements of reactions separated by the supports, whereas there are four conditions of static equilibrium because of this additional hinges. Statics to restrict the external forces, 3 from the equilibrium equations plus 1 from construction. This means that number of unknown elements of reaction is one fewer than independent equations of statics available for their solution. Therefore, the equations of statics for the four systems are generally not satisfied. The beam is statically unstable unless we provide at least one support element. Unless we provide one additional element of reaction, such as additional roller support shown in this figure E or F. Additional element of reaction, which makes the total number of unknown elements of reaction equal to the total number of independent equations of statics needed to determine the elements. If this is done, the beam will be restored to statically stable and determinate state. Next, let us suppose that a roller is introduced into the section of a statically stable and determinate beam. Link is introduced. Link or a roller. We expect that this beam will be less stable than one with hinged connection, because the link roller cannot resist both moments about the link pin and forces normal to the link. The beam will collapse under general types of loading as a result of relative rotation. If the force is applied like this, it will move like this, so this has no restraining moment, so it will move like this, it will collapse. The same way here also, if I apply here, what will happen? About this point it will rotate. From this one it will rotate. From this one it will rotate like this. So the link roller has no capacity to resist lateral forces. Or moments. So if we add some hinged two support reactions, here also two support reactions, it should not have caused lateral to slide. So it is having two releases. The link either of 2 points, H is the sum of the forces on either side of the structure. No, it's not satisfying the moment of the structure either side of the link that is not rotatable links. Okay. Here you see beam is unstable not because of the inadequacy of the supports but because of the inadequacy of the arrangement of members. Internal geometric stability. If number of reaction is less than condition plus 3, that is statically unstable. If number of reactions equal to condition plus static equilibrium equations, then beam is statically determinate provided that no geometric instability in internal and external is involved. If R is greater than C plus the beam is statically indeterminate. Here we will see R, number of reactions 2, 3, 4, 5. 5 reactions plus 1, 2 conditions. 5 plus 2 is what? 5. Okay, 5 reaction equal to condition is 2 plus 3. 5. 5 equal to 5, stable and determinate. R is nothing but the number of reactions. C is nothing but number of equations of conditions. Conditions, that means internal hinges. And plus 3 is equilibrium equations. Okay. C equal condition hinge 1 for roller 2. C equal 0 for beams without internal hinge. So here if I see it's a 2, 3, 4, 2, 6. 6 number of reactions are there and 2 conditions are there. So 2 condition means 2 plus 3 equal to 5. So 6 is greater than 5. Number of reactions is more. It is stable and indeterminate for first degree. If you go here 2, 2, 1, 5. Here 1, 2. This is equal to 5, but it's unstable. Why? It is rotating about this one. Both are equal, that means it should be stable and determinate, but it is unstable. Even though it is determinate, it's unstable. Here you can see because of these 2 hinges, if some load is applied here, it will start rotate, move upward. So this is unstable structure. Here 2 fixed 2 internal hinges are there because of it. And here also if we see internal geometric instability, this is because of internal geometric instability. Possible form of displacement is indicated by dotted lines. So here if you see it 2, 3, 4. 4 is the reaction and condition if I see 1 and this is hinge. 2 numbers are coming. So total 3 plus 3, 6. 6 is number of conditions but reaction is less, so it's unstable. And here also if you see it's one internal hinge and this is the roller. So 2, 1 is hinge and C is roller, means it can roll like this and rotate like this. That's the roller. Okay. So here 3, 3, 6, but 1, 2, 2 or 3 is additional. So start stable and determinate. What does this mean, right? If you apply load here, it is fixed here. If I apply load here, it is roller and this is pinned, so it will not rotate. So here if I see 3, 4, 5, 6, 7, 7 reactions, but here 1, 2 plus 3, 5 conditions, but still the reaction is more, but it's unstable because of internal stability issues. If I apply load, it will move like this. So whenever this pinned and immediately some roller is there, if you have support, it's not a problem. Otherwise, fix, especially fixed support, even if it is here like hinge support, apply load, it will go like this. So that becomes unstable like this, I'm telling, but it's unstable.